Alrighty, we're going to continue on with radicals today. We're going to finish up this chapter. Important thing to note that remember this chapter and your spectroscopy chapters are put together. So for your next exam, for exam 3. So keep that in mind. You're going to have this chapter and spectroscopy. And today we are going to start alkenes, but that's not going to be on this next one. All right, so that'll be on exam 4. So let's continue on. Remember that radicals we talked about various things with that. We're going to learn a few more techniques. So last time we saw we could take bromine in the presence of light, and we end up selectively brominating this position. The point of doing this, by the way, remember chlorinating not so useful because it's not as selective. We're going to see that we can say put in, I don't know, how about some E1 conditions here, and we can get an alkene out. So there are reasons for doing this. This is kind of the only way to kind of activate alkanes. Alkanes are terribly unreactive. They don't do anything. They're solvents. However, under the right conditions, they can undergo these radical reactions to then provide us with an alkyl halide that then we can do all sorts of other stuff on. We can do substitution, we can do elimination, and then from there we can start doing like actual reactions. So typically this is just used as kind of a way to make something not reactive actually start being reactive. So it's really one of our only ways to do it. We have a few more important radical reactions. We saw that with radicals there was 6 different steps, and we looked at 4 of them. We saw there was the homolytic cleavage, which is our initiation of a radical reaction. Remember, we have homolytic cleavage. Give us 2 bromine radicals, or chlorines, or whatever we happen to be using. This is homolytic cleavage. We saw that we could have a hydrogen abstraction. We can have a hydrogen being grabbed away. Remember, we use the fishhook arrows for these. And make sure, again, your arrows are following the correct procedures. Your arrows should be pointing to either an atom or a bond. If it's pointing to an atom, you're going to form a radical on that atom. If you're pointing to a bond or a space in between 2 molecules, like we are doing here between the, because actually we should be reacting the radical, not that lone pair. Whoops. Notice that these 2 fish arrows are pointing at a space in between the 2. That's indicating we're going to be forming a bond there, which is why the products for this reaction are going to be the radical there, because that arrow pointed at that carbon, plus HBr. We have formed a bond in between H and Br, remembering that a bond is 2 electrons. So this was hydrogen abstraction. And remember, after that, we can go ahead and do halogen abstraction. So notice, again, we're going to have very similar arrows here. We're going to have one arrow from our radical forming a new bond. That's the new bond that's going to be taking place. It's going to happen with that radical and that bromine on the left. The other electron here goes onto this bromine, so that bromine becomes a radical. So we have a bromine radical as the other product. All right, this was halogen abstraction. There were two more propagation steps that we haven't looked at yet. And those are going to be important when we look at our next reaction. Actually, I guess, no, I want to do NBS first. Regardless, we'll still see the elimination and addition shortly. So remember, if you have a double bond, and let's just say we have a Br, doesn't really matter what our radical is. Remember, we can add to a pi bond. This is addition to a pi bond. And notice again, look at the arrows. We're forming a bond between this pi bond, the carbon here, and the bromine. And we're also forming a radical. So we are forming a radical here, and we're going to form a bond to bromine. How do we know that's the case? Well, if we did the arrows the other way, this way, by the way, is not going to happen, but we'll see that in a minute. But I'll show you anyway. What would those arrows look like? So we know that this is a addition to a pi bond. If we moved it that way, that tells us that we're going to be putting the bromine on the tertiary carbon. Oops. And we're going to end up with a primary radical. So we're going to see that this isn't going to happen for this type of process, and we'll look at that a little bit later. But for this reaction, notice how the arrows are displaying the mechanism for why we end up with a radical on the tertiary carbon versus the primary carbon. So always make sure your arrows are showing why you get one product over another. So this tells us, because the radical is going here, that means the bromine is going to the other side of our molecule. So that's why we end up with the bromine there. All right, so make sure your arrows are good. So again, this one is not something that's going to happen. Anyways, this was addition to pi bond. It's going to be what we're going to look at with one of our reactions today. And then we have the reverse process, which is what would happen if we formed this one. We would say, well, we're just going to go ahead and eliminate this. So we're going to go ahead, take one of the electrons from this carbon-bromine bond, move it to form a double bond with that radical, and the other electron goes onto bromine. That's what the arrows tell us. The opposite process here, and notice we have a bromine radical now. This is elimination. Elimination to form a pi bond. And then our last reaction that we covered was coupling, right? So that would just be any manner of examples where we just take two radicals, form a bond in between them, and we're done. This was coupling, which is a termination step. So all these elimination, addition to pi bond, all those are because it's radical. Yeah, that's why. So let's look at this more closely. The bromine has three lone pairs, right? And its octet is satisfied by the fact that there is a bond to carbon. When we split this, homolytically, we can say, this is two electrons, right? If we were going to split this homolytically, one electron goes to bromine, one electron goes to carbon. So the three lone pairs are still there, and it gets just one electron from the bond that it's shared with carbon. So carbon has technically 7 electrons as well, right? It's got 3 bonds. Those 3 bonds are each 2 electrons, and it's got the 1 radical. So all radicals are odd electron species, so they will always have 7, 5, 1 electrons, some sort of odd number of electrons. So that's why bromine radicals will have that. All right, so fun stuff. So that's why. So so those were the 6 kind of steps, right? So let's take a look at something like this. We're going to see shortly later today, because this is chapter 10, it's assuming we've already covered the others. We're going to see that, unfortunately, with something like this, we can't do. We might expect that we're going to form the allylic position radical and make a nice, happy allylic bromine. But we do have a competing reaction here. We're going to see later on that really what's going to happen is we might expect something like this, a allylic position to be halogenated, right? Because allylic radicals would be more stable than tertiary ones. And we saw that bromine selectively will go for the most stable radical. But we have a competing reaction. We're going to see that we have a competing reaction here where we put both bromines where the double bond used to be. So we're going to see here that this is not a great reagent for getting this allylic bromination to happen. We will end up dibrominating our cyclohexene into dibromocyclohexane. We'll have a racemic mixture of the anti-product. But we'll cover that reaction later. But suffice it to say that as a result, there was research into figuring out how can we get this to happen without this side reaction. We see that we can do the same thing using a different bromine source. And this will give us our brominated species, technically racemic. NBS is N-bromo succinimide. That looks like this. Make this super clear. So it's a 5-member ring. One of the members is in nitrogen. We have 2 carbonyls, and then we have on the nitrogen a, 'nitrogen, 'a' 'nitrogen, 'a' 'bromine. 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 'Nitrogen, 'a' ' And so with light, we end up homolytically cleaving, forming the nitrogen radical. Nitrogen radicals are more stable than others. We have one in our bodies, nitric oxide. This dude, important hormone for us, a simplest hormone, just two atoms. It causes our blood vessels to dilate. So nitrogen radicals are fairly common. So I'm going to say stable with quotation marks to indicate that they're relatively stable. They're more stable than others. And of course, we will end up with our bromine radical. Again, it has 7 electrons. That one, of course, is not stable. That one's going to go ahead and react with things. And we see, aha, well, now we're going to have a lot of this NBS in here. So we'll end up, say, taking off, just for the purposes of reaction, we'll make it simple. We could have this go with a bromine as well. It doesn't really matter, but we're going to go ahead and just do it with this radical. So we're going to end up doing a hydrogen abstraction onto the succinimide radical. And I have no space, so I'm just going to do this down here. So we'll have our radical here, and then we'll have succinimide. This radical now, we'll see our dear friend the bromine and can couple with it. Or it can see other, actually we can say, we'll say NBS. We'll see another NBS molecule because we want to do a propagation really. We don't want to couple this right away. Say that this is a side product. Okay, here we go. So we're going to form another succinimide radical, and we're going to have brominated our cyclohexene. Could be wedge or dash. And then we make another, since we are propagating, we're still going to make another radical, which can then go and take off hydrogens and stuff, and we can have things keep on going. So how the NBS process works is it prevents that problem of dihalogenating. If we were to just use Br2, we have a competing reaction. If we use NBS instead, it will only brominate the allylic position. So NBS selectively brominates positions. So plain old Br2 goes on tertiary, can go on secondary places, not a problem. NBS will only go on allylic or benzylic positions. So it's more selective. It will only go on those. And so if you have something like this, we're going to see we can end up with multiple products here because of resonance as we go through. If we go ahead and say, yeah, we're going to go ahead and do some NBS on this stuff, we have multiple allylic positions, right? You can brominate here, you brominate here, Actually, I guess I have to do this separate because we're only going to get usually one position brominated. And then we have technically also the other side. So we have these three products, but we also could get something like this if we resonate. Excuse me. You can have all sorts of things happening here. So if we have multiple allylic positions, or that allylic position can resonate, because if we look here, say we made that uh, radical there, we can resonate. If we resonate this, we now have this, and then now we can say, aha, now our bromine is going to come in, and now we're going to have it over there. So now it's on this one. So this is a product, an additional product. So just depending where you make your radical, it can resonate, and so you may end up with more. And both of these are pretty stable. Yes, you have a tertiary allylic versus primary allylic. They're both really stable. They're both really stable, so you will get a mixture of products. So just beware of that. Right? So a mixture of products possible. In this case, I illustrated both at once. Multiple different allylic spots. And, or if we can resonate it. So we resonated with resonance arrow in between. These are resonance forms of the same structure. We can then brominate from either one of those. So we can get either position, either resonance. So we're going to get a whole mess of products. That's the point here. Because this one has three different spots to brominate regularly, and then it can resonate also. So we have even more. So we got lots of various places we can resonate this. So in fact, we're going to have 6 different products. 3 different spots to 3 different allylic hydrogens to go ahead and abstract, and also 3 different resonance forms of each of those. So we have 6 total products out of this reaction. So just be aware of that. So if you are going to do a radical process and you have the possibility of resonance, you need to keep that in mind. So it'd be hard to say which position would probably be the best. I would say that this very last product is probably the most common. Actually, maybe not. Because the thing is, you end up with, you have your most stable radical, right? Tertiary allylic. But you don't end up with the most stable product. You have a mono-substituted double bond. So maybe it's better to just brominate on one of the positions, and really there's no difference then as to which one of these you brominate. So hard to say. However, very specifically, with benzene-based ones, you do not have the resonance happening. If you put NBS here, you're not going to mess with the benzene. It stabilizes the radical, but you're only ever going to have it brominate the benzylic position. This one's not going to resonate. Because if you do resonate and then brominate, you're going to end up breaking the benzene's aromaticity. That's something we'll cover next semester, but we don't end up reacting resonant radicals here. Simply because the resonance forms are not nearly as stable as just putting the benzylic radical there. So it can resonate, but they're just not as good. So uh, for a benzylic one, we're only ever going to get the benzylic position. So we're not going to have to worry about it resonating and then brominating in various other spots. So that's kind of what we're looking at here. All right, so that's NBS, selectively brominates allylic positions, but then just beware resonance may give you a multitude of products. In this case, we only get one product. Okay, well, that's not quite true, is it? We get a receiving mixture, so two products technically. Miss Jersey, what are you eating? I think she's eating like cardboard. Oh well. All right, so that's NBS, N-bromosuccinimide, selectively brominates allylic positions or benzylic positions, and it's a great way to do that because you avoid problems with just plain old bromine or with alkenes. All right, and the last one is addition. Is going to be a pi addition. So we're adding to a pi bond. And since we're about to cover alkenes, I figured I'll just cover this one now while we're still on the radical idea. Um, what's interesting here is we're going to see that normally if we do this reaction, we will add these uh, like so. However, in the presence of peroxides, we end up doing the opposite. And this will be very useful for us uh, once we talk about these alkene reactions. We're going to study this one later, and we're going to see why. The first one proceeds through a carbocation mechanism. The second one goes through a radical mechanism. And so we're going to see what these look like. So for this one, this is called an, I don't want to say it yet. I'll tell you later. I want to focus on the mechanism and why this happens because it's radical chemistry. So, first step for this mechanism, always for a radical process, first step is initiation. And that's where these peroxides come into play. Because the OO bond is particularly weak, you end up having some homolytic cleavage. You don't even need light, it just happens spontaneously. And you get two of these oxygen radicals. Unpaired electrons are radicals, right? So we end up with that. What happens are propagation steps. We're going to first have uh, some reactions happening between the HBr and the peroxide. We're going to see we're going to produce a bromine radical and some alcohol. Bromine radical is the important part. Remember, propagation, you start with a radical, you end with a radical. Now, this is hydrogen abstraction, by the way, if you can't tell. We have our bromine radical. We have to consider, remember, we looked at this a little bit earlier. Sorry, wrong color. Um, we saw that when we attack this, we can either put the radical on the tertiary or on the secondary position. It's always going to go onto the more stable one. So we're going to end up putting our radical onto the tertiary position. And so we're going to form the CBr bond between the other two, thereby giving us our tertiary radical stabilized. So this is addition to the pi bond. And we're not going to eliminate this time. What we're going to do is we're going to have another HBr molecule come along. I forgot my radical. There we go. And we're going to have that react with the H. So that one's going to now undergo hydrogen abstraction. And we're going to go ahead and, we're going to now have the H there and the bromine. So we end up doing a second hydrogen abstraction. Because this is propagation, we end up with another radical. That's another bromine radical, which now can go ahead and do more reactions. So this just keeps chaining, it's a chain reaction. As soon as we get that initiator to do its thing, we make our first bromine radical. That bromine radical makes a carbon radical. The carbon radical then makes a bromine radical, and back and forth. And now this bromine radical will go and back and do the same thing with another alkene. All right, and then if we have some termination steps, and I'm just going to show the only productive termination step. When that leads to our product, we can just couple. And we will make our product. I guess this one already had a bromine on it, but oh well. Okay. This would be an example of a coupling reaction. Remember, the coupling ones are not the major parts. It's side products we get. Like we could take two of these with, we could have it with an oxygen radical as well. These don't necessarily have to be productive, but we end up with these kind of side products, by and large, from termination steps. We could have bromine coming together with another bromine as well, things that remove our radicals from the process. So our propagation step is the one, again, like before, that give us the product of interest. So it's these steps over and over and over again that keep producing our product. All right, so the main idea here is that your radical will go to the more stable position. Right, and so that's going to be the tertiary one. Right, and so that's how this is going to happen. So we have first initiation, breaking this apart. Our first step of making a bromine radical is a propagation step. So we have our peroxide radical attack a hydrogen bromide, making an alcohol and the bromide radical. The bromine radical then can add to the double bond, add to a pi bond, creating a radical, which can then abstract a hydrogen, producing another bromine radical. That bromine radical now finds another alkene and adds to that double bond, producing a radical, which then goes and grabs a proton, producing another bromine radical, and so forth, until we start some termination steps happening. So again, propagation is where we're making our product of interest. Termination typically is side products. Typically, we don't see hydrogen radicals as much. They're usually less stable, so we don't typically have termination steps that use hydrogen radicals. Otherwise, we would do that. So, all right. So that's the idea here. That's what's happening. This only happens with HBr in peroxide, by the way. It does not work with hydrogen chloride. It does not work with hydrogen iodide for various thermodynamic reasons. Suffice it to say, it is only thermodynamically favorable with bromine. And we saw that NBS is only with bromine, and bromine is the only selective one. So that's the winner of the day. So bromine is really the big player in our radical chemistry. So bromine radicals are the winners here. So whichever way we're putting them on, if we're just putting them onto an alkane, Br2 is better because it's more selective. If we're putting them onto an allylic position, we need NBS. And if we want to add them to an alkene, onto the less substituted carbon, we're going to use HBr in the presence of peroxides. We just need the peroxides there to initiate the reaction because they're so unstable. They will just start the reaction. We don't need light or anything. HBr is not really something that forms radicals very easily anyway, so you need something else to help it along, and that's the peroxides. They found this out, by the way, because there would be peroxide like residues in some of their solvents and things, and as soon as those were present, they noticed that they were getting the bromine on the less substituted side of the alkene, and that turns out to be a very enormously useful thing to have in your toolkit. Okay, cool. So let's. Now I'll give you practice problems on this, so we'll spend the time here on alkenes. Okay, so that's it for radicals. There's some other stuff about polymerization and all that. We'll talk about those next semester. We're not going to really talk about them now. So that's it for radicals. So just remember, spec is 14 through 15. Let's talk about that exam. And when are we going to do this exam? Next week, too early? Yeah, we just did one. I don't want to create another one. That said, though, we are done with the material. Yeah, let's do the 15th. Will be nice. We'll have this on 11:15. We will have 2 or 3 spec problems, which means you're given you're going to be given those 3 spectra, figure out the structure. You may have some conceptual NMR stuff. So conceptual not meaning like I don't need you to build me a machine or something like that. Um, to understand splitting patterns, for example, or why something might be de-shielded, why it would show up more downfield, things like that. That's more conceptual NMR stuff. And then you'll also have some radical chemistry. So by and large, we're looking at about, I would say, 66% will be spec, and the other third will be radical stuff. So with the radical stuff, we're looking at we've got splitting, we've got things like that. With radicals, what we're looking at, we have mechanisms. So just like with our last exam, we had that what was it? It was an E1 reaction. We did a mechanism for, and we showed some carbocation rearrangements. So we can have some mechanisms there for radicals. It's off somewhere. Where's she going? Um, we can have some predicted products. And let's see, what else can we do? We can have some kind of like determine product ratios. So remember, like, why we saw, like, what's the ratio of, if we were to chlorinate this thing, what's the ratio that we would have the secondary one chlorinated or the primary one or whatever. So that's kind of the stuff we're going to be focusing on with radicals. Okay, so the mechanisms, everything we've talked about in these last 2 days. Um, so that'll be the halogenation of alkanes. For today, we talked about NBS and we talked about the HBr halogenation as well onto an alkene. So we have two more that we studied today. And all of these, remember, bromine is the winner. So um, we'll work on that. All right, so we're going to, in like 2 minutes, start alkenes. I'm just going to go check where little Miss Bailey has run off to. And I'm going to stop the stream so that way it's hopefully more clear that we have kind of two chapters. So people who are watching this on the 14th, because they've waited this long to do it, we'll do it later. Okay, so we'll have a separate video in a few minutes. I'll start that one up for just for the remainder of today. Okay, so look for that in just a sec.